Ranger 2, prepare to detach.
What? No! No! Cooper!
3.
Cooper, what are you doing?
Newton's third law. You gotta leave something behind.
As I had another question in the middle of the night. So this is I can't remember which paper it was now. AQA 2024 AS Paper 2. So question 3. So figure shows an energy storage system uses a load suspended from 2 long cables in a vertical tunnel. Okay, so the energy stored when the load is raised, electricity is generated when the load falls. Okay, so when the load is at its lowest point, each cable has a vertical length L. Okay, so the total mass of the 2 cables is 3.7 times 10 to the 4 kilograms. Each cable has a cross-sectional area of 9.6 times 10 to the minus 3. Calculate L. Density of steel is this. So what formula are you going to use here? Density is mass over volume. To work out the volume of a cable, so it's the cross-sectional area, which they've given here, and times the length, isn't it? So V is equal to cross-sectional area times L. So we could put that into here. So rho is M over AL, and we want to work out L. So L is M over rho times A. Okay, so just be careful here. They're given the mass of 2 cables, so you want half of that. 3.7 times 10 to the 4 over 2 over the density, which is 7.4 times 10 to the 3 times by the cross-sectional area of 1 cable, so 9.6 times 10 to the minus 3. So when you put all that in, I got 260.4 or 260 meters. So that's just be careful with that one. They gave the mass of 2 cables. Okay. Right, so what we got here, load is accelerated from its lowest point. The mass of the load, so if I sort of draw the picture, so we've got the tension upwards, the maximum tension in each cable. So you've got here 2T. Then we've got to look at what we got down here. So we've got the mass of the load, okay, plus you've also got the mass of the cables. So mass of the cables, and there's 2 of them. All right, and then you're going to times both of those by G. All right, so let's do, well, what is the total mass downwards? So let's do that one first. So you've got 2.8 times 10 to the 5 plus 3.7 times 10 to the 4 times by 9.81. So when you put that in, I'll just put the whole number down for the time being. 9770. That's total down. Now the total up is 2 times 1.6 times 10 to the 6, which is 3.2 times 10 to the 6, and that's the total up. So we can work out the resultant force is simply 1 minus the other. So if I do 3.2 to the XP6 minus answer, so the resultant force is 90,230 newtons upwards. All right, so now we've got to work, the resultant force equals MA, and then A is the resultant force over M, so it's 90,230 over the mass of the load plus mass of the cables, because that's what's getting accelerated, so we're looking at that number there. Okay, so when I put all of that in, that gives me 0.28. Okay, so that's how you do that one. So let's move on to the next question. So for safety, the breaking stress of each, so stress is force over area of each steel cable must be at least 3 times the maximum stress produced during the initial acceleration. So the breaking stress for steel is this, so deduce whether this system operates safely. So what do we know about the tension in the cable? The tension is 1.6 times 10 to the 6 newtons. So that is the force on the cable. And we know the area, cross-sectional area of the cable was 9.6 times 10 to the minus 3. So you can work out the stress is simply force over area. So if I put those in, so I get 1, 2, 3, 4, 5, 6, 6, so 167 megapascals. Okay, so then if I times that number by 3, so times by 3 equals, so so if I put that in, sorry, so 3 times that, so that gives me 500 megapascals, which is less than 890 megapascals. Okay, so it's pretty safe. All right, let's move on. What on earth is going here? So village combines the storage system with a wind turbine to provide energy. Figure 12 shows how the output power of the wind turbine, which is the bold line, varies with time during one particular day. Okay, so from midnight okay, so the power demand of the village is seen, so yeah, so that's when people are at the house, I guess. Well, what's going on here then? So when the power demand is greater, the output power of the wind turbine, the load in the storage system descends and generates electricity to match the demand. When the load has fully descended, the storage system is empty, electrical power is provided by a national grid. The efficiency of the energy transfer from the storage system to the village is 85%. The maximum energy storage by the storage system is 760 megajoules. Right, so deduce whether the storage system and the wind turbine can together provide all the electrical energy needed by the village from 10 till 2. So 10 o'clock in the morning to 2 o'clock here. There's 2 o'clock, 14, yeah. So 10 a.m. to 2 p.m. So what we can do for a start, let's work at the storage system is 85% efficient. So let's work out 85% of 760. So 760 megajoules times by 0.85. So let me just put that in my calculator. So that's about 646 megajoules. Now what we've got to do, it's a bit of a weird question this. So between 10 and 2, we've got to work out what they actually needed. So we've got to work out that area there. Now you're probably thinking why area, because power times time gives energy. So energy is PT. So in this case, it's the area under the graph. And then you could actually work out the area of the wind turbine. So you can work out the energy of that. Just be careful with the units. And time, you got to convert that to seconds. And then add the 646, and we're going to compare. Okay, so let's work out for the demand, and I'm doing all the calculations here. Obviously, you've got to do it at the bottom. So the demand, now if you look, right, okay. So you've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 11.5 squares. Okay, and then what each one, I mean, you just work out the area however you want to do. You want to do shapes, triangles, rectangles, that's entirely up to you. Now, if you look here, 1 square, so that's 50 times 2, isn't it? So is it 2? So that's 2. Is that 2 hours? Yeah, it is. So that's 2 hours. So this is 50 times, so that's 100 kilowatt hours. That means that is 1150 kilowatt hours. Now, if you look at the the wind turbine, just wind turbine, yeah. So how many squares is that? 1, 2, 3, 4, 5, 6, 7, 8. Oh, great. So you will probably have to work out the area of this one, I think. So 1, 2, 3, 4, 5, 6, 7, 8. So you got at least 800 kilowatt hours, and then probably work out this little triangle here. So that's 50 times 2 and divide by 1. So that's 100 kilowatt hours. So that is, of course, 900 kilowatt hours. Now what we've got to do, we've got to convert this megajoules into kilowatt hours, add it to the wind turbine and see if it is equal to, greater than, or less than 1150. So if you remember, 1 kilowatt hour was equal to 3.6 megajoules. If you didn't know where I got that from, kilo is 1,000, hours is 3,600, energy is power times time, so that gives you 3 million or 3.6 megajoules. So I'm just going to divide this number by 3.6. So that is 179 kilowatt hours. So if you add that to here, 179 kilowatt hours. So that gives you, so plus 900, okay, 1079 kilowatt hours. So no, doesn't meet demand. Now, all these calculations that I've done and my conclusion, of course, you've got to put into here, okay? Actually, if you leave it there, they should be marking it anyway.